Now that we have this fundamental theorem of analytic functions, we can compute path integrals much easier. We just have to look at the primitive and then evaluate the primitive at the end of the path minus the beginning of the path. Now, this also means that if you're looking at simply connected domain and the path is a loop, then the loop will start and stop at the same location. So that means that the path integral will be always 0. But it does have to be simply connected in that case to make that conclusion, because otherwise we might not have a primitive. Okay, but actually, even if there is a hole inside of the domain, you could use this theorem in a creative way to make the computation much easier. So let me describe how we're going to use this. Okay, so let's say you have two paths, gamma 1 and gamma 2. And let's say these paths are simple closed loops. So that means it's a curve that does not intersect itself, and it's oriented counterclockwise. So imagine a picture that looks like this. Here's an example that I'm going to compute in a second. We have two paths, gamma 1 and gamma 2. One is on a circle and one is on a square. So depending on the integrand, one integral might be much easier to compute with a particular path. You might not have a simply connected domain. So if you have a function 1 over z, for example, then there's it's undefined at the origin. So you can't just conclude that there's a primitive and the integral is equal to 0. But what you can do is compare the path integral as long as the domain between the two curves has no holes. So what I mean by that is that we could divide up these two curves into, smaller path using the same technique as we use in the proof. We could look at a path that looks like this. Let's just break it up into 4 pieces here. And if we do it, compute, you could break up the path into these 4 smaller pieces. These curves, 4 curves, is defined on a simply connected domain, right? So you could define it in this domain with avoiding the hole at the origin. So that means that the path integral on that small segment is equal to 0. Because now we can use Gorsat's theorem and the fundamental theorem of analytic functions. And you could do the same thing with all 4 of the pieces. Okay, all of those path integral is 0, which means the path integral on the outside minus the path integral on the inside, which is equal to the sum of the 4 smaller pieces, is equal to 0, which is equivalent to say the path integral on the square and the path integral on the circle is exactly the same. So if you have a path integral like this that I want to integrate over the square, it's actually much easier to integrate on a circle radius r, because you can parameterize those with r times e to the it. It's a parameterization we use for the unit circle rescaled by constant r. And we've actually already done this computation in the past. The path integral, in this case, it's not 0, it's 2 pi I, but we know it's equivalent to the path integral of the rectangle. but we just chose circle because it's easier to integrate. And we know that they're equivalent because the domain is analytic in between those two curves. So I could slowly deform any path, closed path. You can kind of think of it as a rubber band, change it into a path that's convenient for us, and do that computation. Okay, another example. Let's say I have the integrand 1 over z squared plus 2z. If we do partial fractions, we can understand the function a little bit better. It's 1/2 over z minus 1/2 over z plus 2. So this function cannot be defined at 0, and it cannot be defined at, negative. It cannot be defined at -2. Because then z plus 2 is divisible by 0. Okay, and let's say I want to integrate on the unit circle this way. Okay, what we could do is we can break this up into, so since we broke it up into two functions, we could do path integral separately. And since this function z plus 2 this is only defined, undefined at z equals -2. This thing is perfectly finely defined at z equals 0. This function is defined on a simply connected domain, avoiding the -2. So by fundamental theorem of analytic functions, we integrate, it's closed loop, it's equal to 0. We get that immediately. And then 1 over z, so this does like a loop over the undefined point 0. So you do have to integrate, but we've already done that computation. It was 2 pi I. So because of the 1/2, we get pi I at the end. Okay, so what simplified the computation there? So we had a function where two bad points. There was a bad point at 0 and -2. You broke it up into two functions where one function is bad at 0 and one function is bad at -2. The path only circled one of them at 0. So we were able to simplify the computation for the other one. Okay. So this really dramatically changes the way we think about path integral on loops. We should think about path as kind of rubber band topological curves that we can flip. We could change it in a flexible way, as long as the integrand we have is analytic. So we're gonna use this idea further to prove some incredible integral formula next time.